Hey kids, welcome to section 2.2, linearity and symmetry. Today you're going to learn how to identify linear and nonlinear functions by examining equations or graphs, and also how to determine whether graphs of functions have line or point symmetry. So first, let's talk about how we can identify linear functions. That's what this chapter is all about. So first, in a linear function, no variable is going to be raised to a power other than 1, which means you're not going to see any powers. It can be written in the form y equals mx plus b or ax plus by equals c. We're going to learn the second one if you haven't already. The first one should hopefully look familiar. That's slope-intercept form. And the graph is a straight line. So if you look at a picture, it's going to be a straight line of some sort. That's a linear function. Notice the word line in linear function. Okay, in a nonlinear function, this means no line. The graph includes a set of points that cannot all lie on the same line. You cannot write it in the form y equals mx plus b. An example might be a parabola. This is a nonlinear function. That's a parabola. You can also have an absolute value function. That's also a nonlinear function. So that's kind of what the visual looks like and a little bit of the equation. Here's what some examples might be of the function. So a linear function can be written in the form f of x equals mx plus b or y equals mx plus b. Notice that all the good examples, let's see, we have y equals negative 2/3 x plus 1, y equals 1/2 x. If you were to solve this other equation by minusing 4x and then dividing by negative 5, we can also write this one. So that'd be a positive 4/5 x minus 16/5. So it is able to be written in y equals mx plus b. If you look at the non-examples, the first one, f of x equals 1 over x, you are not allowed to have variables in the denominator to be a linear function. Second example, 2x plus 6y squared equals negative 25. Notice the square. You can't have any powers greater than 1. And x plus xy equals negative 5/8. You can't have two variables being multiplied together in a linear function. So let's look at some examples. Try to decide if they're linear or not. State whether each function is a linear function and justify your answer. If yes, express the equation in slope-intercept form. So basically, if you can write these equations in y equals mx plus b, then you have proven that it is a linear function. So let's try to write them in y equals mx plus b. Okay, so in this first equation, 3x plus 2y equals 8. If we try to solve for y, we're going to subtract 3x. So 2y equals negative 3x plus 8. Divide by 2. Y equals negative 3 halves x plus 4. So yes, I can write it in slope-intercept form. So yes, this is a linear function. And write it in slope-intercept form I did. Letter B, f of x equals 2 over x. Remember, this is y equals 2 over x. And right away, you cannot have a variable in the denominator. So this is no variables in denominator. If you were to graph that, you would not get a straight line. That's the other thing you could do. You could plug it into your calculator and see what you get. You're going to get something funky. It kind of looks like this. Okay, letter C, y equals 3xy minus 4. Boom, right away you have two variables being multiplied together. So this is not a linear function. Can't have product of two variables. It will not give you a straight line. It'll give you something more like B. Letter D, 5 over x plus 6. Again, not linear, no variable in the denominator. So we'll say no variables in denominator. All right, letter E, g of x equals negative 3 halves x plus 1/3. Remember, this is y equals, and this is already written in slope-intercept form. So this is yes, and we'll say already in slope-intercept. Y equals mx plus b. Okay, letter F, k of x equals 2. Remember, this is y equals 2, and that already is in slope-intercept form. So this one is linear. Remember, if you just have a single letter equals a number, that single letter is the axis that it goes through. So this is going to be a horizontal line side to side through y at 2. And we'll say y equals 0x plus 2 is technically your slope-intercept equation. Okay, so that's looking at function equations and seeing what we can tell. Let's look at pictures and tables. So example 2, it says the graph models one prediction about the population of the northern snakehead fish in a lake over time. The data in the table models a second prediction. State whether each is a linear function and justify your choice. So notice in Model A, they have after 0, 1, 2, 3, and 4 years, just what the population is going to be. Model B has 0, 1, 2, 3, and 4 years, and what the population is going to be. So let's look at Model A. Our job is to determine if it's a linear function or not. And if you notice, the dots do not form a single straight line, so this is not linear. Graph is not a straight line. If I look at letter B, well, it's just a table. I have no idea, so I'm going to draw a graph, a really quick sketch just to give me a visual. So we have 0, 1, 2, 3, and 4 years. Again, doesn't have to be pretty. And then we're going from 100 to 200, so I'm going to go 50, 100, 150, 200. Okay, so 0, 100, be like right here. 1, 125, 2, 150, 3, 175, 4, 200. That looks like a straight line, so I'm going to say linear. When graphed, data forms a straight line. So you can draw your own picture to be able to state if the function is linear or not. All right, let's look at another example. Shayla and her brother Malcolm both left home on their bikes at the same time. The graph shows a function modeling Shayla's distance from home over time. The table shows a function modeling Malcolm's distance from home over time. State whether each function is a linear function and justify. So it looks like Shayla starts off at home. She rides for 10 minutes away, 20 minutes away. At 30 minutes away, she turns back around and is going back home again. I don't know what Malcolm's doing, so we should probably draw a quick sketch of his. 0 to 40 minutes again, so 10, 20, 30, and 40. And 0 to 6, so 1, 2, 3, 4, 5, 6. We'll go 2 and 4 and 6. Okay, so 0 and 0, 10 and 1.5, 20 and 3, 30 and 4.5, 40 and 6. Well, it looks like Malcolm just keeps getting farther and farther away from home. Shayla turned back around. So it looks like Malcolm's going to need a ride home. All right, so Shayla, her graph is definitely not linear. She's more of an absolute value. We can say the graph is not a single straight line because you need to have a single straight line, not a V-shaped line. If we look at Malcolm, his graph is a single straight line. His is a linear function. When graphed, data form a straight line. Okay, so that visual. When in doubt, draw it out. Okay, so now we know visually a little bit more about functions, not a function. Let's talk about something called symmetry. We have two different kinds of symmetry that we're going to talk about. The graph of some functions exhibits something called symmetry. The graph of a function has line symmetry about a vertical line if each half of the graph maps exactly to the other half. So you have a right side, you have a left side. If you were to fold them up, they would meet. The vertical line dividing the graphs into matching halves is called the line of symmetry. So that actual line has a name. And each point on one side is reflected over this line to a point equidistant from the line on the opposite side. Okay, I'll show you what that means in a second. If you look at letter A, state whether the graph of each function has line symmetry. If so, identify the line of symmetry. So in letter A, you want to try to find a line that if you drew it down the middle, it would fold the graph in half and make two halves of the same picture. Now it has to be a vertical line, not a crooked line, not a side-to-side line. Letter A does not have any line symmetry. No line symmetry. However, if we look at letter B, you can imagine a straight line kind of going right down here, and every point on the right side of that straight line can be reflected to a point on the left side of that straight line. So this one definitely, yes, has line symmetry. And then it wants us to state what that equation is. So it's going through the x-axis at -2. So x equals -2. If you look at letter C, and you try to draw a vertical line anywhere on the graph, and then fold the right side and the left side up, these will not form mirror images. This one has no line symmetry. So you cannot draw a vertical line and fold it up side to side and have it meet. The other type of symmetry is called point symmetry. The graph of a function may also exhibit a type of symmetry called point symmetry. The graph of a function has point symmetry if it can be rotated 180 degrees about a point so that its rotation maps exactly onto itself. So here you'll be spinning the graph top to bottom or bottom to top and seeing if you get the same exact picture back again. The point that acts as the center of this rotation is called the point of symmetry. So if you look at letter A, state whether the graph of each function has point symmetry. If so, identify the point or points of symmetry. If you were to try to put a dot somewhere on the curve, would you be able to rotate the picture 180 degrees and have it still be facing down? The answer is no. If you were to take your paper and physically turn it upside down, it's not going to be a downward shaping parabola anymore. It's going to be an upward shaping. So this one has no point symmetry. If we look at letter B, and you try to imagine a point and rotate the picture 180 degrees to try to get the same picture, well, I can pick this point right here at 1, 3 and rotate my picture 180 degrees and I'll still get this shape. Guess what, kids? I can also pick the point 0, 1, rotate 180 degrees and I'll still get this upward facing graph. So this one, yes, has point symmetry. And it wants me to name the point of symmetry, and there's actually an infinite number of points, and so we're going to say any point on the line is a point of symmetry. Now that doesn't always happen, but in this case it does. If we look at letter C and we try to imagine a point where we can turn the graph and have it be the same thing, hopefully you can see that at the point 0, 0, I can do that. So yes, point symmetry. And if I use the point 0, 0 as my point of symmetry and rotate my picture 180 degrees, I'll get the same exact picture. All right, so let's put all of this stuff together in this last slide and let's do some last examples. So number 6, Tony tossed a basketball. Below is a graph showing the height of the basketball as a function of time. State whether the graph has line symmetry or point symmetry. If so, identify any lines of symmetry or points of symmetry. So notice that the basketball is starting at a height of 6 feet. That's probably above his head. He's throwing it upwards maybe to make a free throw, and then it's hitting the ground. So does it have any lines of symmetry? Well, I'm thinking that there's going to be a line of symmetry somewhere right here. Because then even though this picture stops, it continues. And so I can fold up the picture and make it match. So this one definitely has line symmetry. And let's see, it goes through the x-axis at 0.4. So that is my equation. Point symmetry. Is there a dot somewhere on the curve that you could then potentially rotate it 180 degrees and have it be the same thing? And the answer is no. Okay, example number 7. Of the 4 equations shown, identify the one that does not belong. Explain your reasoning. Okay, well, if I take a look at these, first thing I notice is this is a straight line, so this one's linear. Ooh, and then if I look at this first one, this one's also linear. It's in y equals mx plus b. Let's see if I graph this one. 0, 4, 1, 2, 2, 0, 3, negative 2. Ooh, that one looks linear. And if I look at the last one, ooh, not linear because you have 2 variables multiplied together. So this one is the one that doesn't belong, and this one is not linear. Okay, number 8. 8A. Which letter has both line and point symmetry? Okay, so can I chop the B in half for line symmetry? No. So therefore it's not it. Can I chop the T in half for line symmetry? Yes. Does it have a point I can rotate it 180 degrees and set the same picture? No, so it's not it. S, is there line symmetry? Can I chop it in half? No. Is there point symmetry? Can I put a dot somewhere and have it twist? The answer is yes, but it has to have both, so it's not it. If we look at H, does it have line symmetry? Yes, if I go down the middle. Does it have point symmetry? Yes, if I put a dot in the middle, so it's got to be H. Okay, which letter below has point symmetry but does not have line symmetry? Okay, well, we said H has both, so that's not it. Does N have point symmetry? Yes, if I put a dot in the middle, I can rotate it. Does it have line symmetry? The answer is no, it doesn't. So, ooh, it's probably N. Let's just look at the other ones. Does A have point symmetry? No, so it's not that one. Does E have point symmetry? No, so it's not that one. All right, kids, that is the end of section 2.2. If you have any questions, please let me know. And as always, keep calm and keep trucking.